Here's the quiz on matter and energy. So at the beginning of this unit, we looked at some early models of the atom. You don't have to spend days and days and hours reviewing those early models and early experiments. It's interesting and it kind of lays a good foundation for what is to come, but it's not a major player on the AP exam. Now, things that might come up are this Millikan oil drop experiment, where in the packet they tell you the exact charge per electron, negative 1.602 times 10 to the negative 19th coulombs. Coulombs is a unit of charge. Now, in this experiment, Millikan had ionized the air in this chamber, which just meant that he knocked electrons off of the atoms in the air. So there were free electrons moving in this air, sprayed a very fine mist of oil into this chamber. The electrons accumulated on the oil droplets, and then he tried to suspend those oil droplets between two charged plates, positive and negatively charged plates, and found that the amount of charge he had to apply always came in a whole number ratio of this. It was always a whole number integer. Oh, okay, cool. So then he was able to figure out how many electrons had accumulated on the oil droplet. And that kind of comes in number 2 then. The total charge on an oil droplet was determined to be negative 4.806 times 10 to the negative 19th coulombs. How many electrons had accumulated on the oil droplet? And all we have to do is divide. So in your packet, they will give you the charge on an electron, and here might be a situation where you would use that constant. It's one of the pieces of information in the equation packet that is rarely used. And it wasn't used at all for the last couple years. Now maybe that means it's going to come up this year, who knows. But it is not very commonly used. And this is the type of question where you would use the charge per electron. Question 3 kind of references the photoelectric effect, where different types of electromagnetic radiation were shined on the surface of different types of metals in hopes that we would remove electrons, and moving electrons would then conduct an electric current. This is where we started to learn that these different forms of electromagnetic radiation carry different amounts of energy. I mean, I could try, red light, blue light, ultraviolet light, and it showed then that each type of electromagnetic radiation had different effects on the surface of the metal. Sometimes we removed electrons and sometimes we didn't. That there was always this threshold frequency, or this minimum amount of energy that was required to remove electrons from the surface of different types of metal. In this case, we have electrons that are first ejected from the metal when the energy of the photon is 3.3 times 10 to the negative 19th joules. And we want to know what the frequency would be. And so I'm using this equation, E energy, which would be measured in joules, equals Planck's constant, H, times the frequency. Frequency would be units of like cycles per second, waves per second, 1/second, which kind of means like cycles per second or waves per second. It could be seconds to the negative first. And so all we have to do is plug and chug. So I think the trick with these little atomic structure equations is just knowing which one to use. So look at the type of data you have. If you've got joules, any data in joules is representing E, energy, or kilojoules. Now Planck's constant is a constant, but you just have to make sure that the energy term jives. So if E is in joules and Planck's constant is in joules, then we're good to go. But if E, energy, would have been kilojoules, then we got to make sure that they're both the same. So then I'd probably want to change my kilojoules to joules. But then the math is easy. I mean, you can use a calculator on this particular question. Oh, pops the answer. 5 times 10 to the 14th waves per second, cycles per second. Good stuff. Question 4, here's the other equation. This is speed of light equals frequency times wavelength. We want to know what type of electromagnetic radiation has a frequency of 6.1 times 10 to the 14th, 1 over second, waves per second, cycles per second. This table, or this diagram, gives me wavelengths in units of meters. So if I can take that frequency and find its corresponding wavelength, then I can just match it up to the chart. So the speed of light is given to me in the packet, about 2.998 times 10 to the 8th meters per second. I have the frequency, I'm solving for the wavelength. Now, with this equation, the unit that you most often have to just double check is meters. My speed of light is meters per second, so when I solve for the wavelength, it's going to come out in meters. Or if I were given wavelength and I needed to solve for frequency, I just need to make sure that my wavelength would then be in meters to match the constant, the speed of light in meters per second. See, I get really close to that visible green light, about 5 times 10 to the negative 7th. And then that's it. I mean, that's it for major calculations, these two equations. Now you could put them together and you could see something like 5. Warning, this is not in a multiple choice question on the current test. This unit test or the AP exam. But this would be a fantastic free response kind of question where you got to put together these equations. Oh, let's see. We want to know what is the energy of a mole of photons of blue light that have a wavelength, of 450 nanometers. No! Obviously, you can use a calculator. This is free response all day long. Free response. Okay, so eventually I want to use this guy. E equals Planck's constant times the frequency. And the question says, what is the energy? So I eventually want to solve for E, energy. Okay, well, Planck's constant is a constant. So I got this guy, that's in the packet, but I need the frequency. Okay, so then that makes me backtrack to this equation. Speed of light equals frequency times wavelength. Well, I got the speed of light. That's in the packet. And what do you know? I have the wavelength. The only problem is that it's in nanometers. I'm going to want to switch that to meters. And so this little conversion is not in the packet. But you might as well kind of get used to it. I mean, write it down someplace so that you kind of remember it. That the conversion between meters and nanometers, I mean, nanometers are teeny, 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 tiny fractions of a meter. So it takes 10 to the 9th nanometers to make up 1 meter. And obviously it's not the worst metric conversion to remember because nano 9. Now obviously you could also do 10 to the negative 9th meters is equivalent to 1 nanometer. Either is fine. And so I get about 4.5 times 10 to the negative 7th meters. And that then I can plug in as my wavelength. So now I got the wavelength, I got the speed of light. I can solve for the frequency. And then once I have the frequency, I can plug that into my second equation. And now I can solve for E, energy. So you can totally see that this would be like a multi-part free response. Now first I need to solve for the frequency. Then I'm going to plug it into the second equation and solve for energy. But now I have to remember that technically this is energy in joules because Planck's constant is in joules, but it's joules per 1 photon. I mean, 10 to the negative 19th joules, it's crazy, 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 crazy tiny. That's per 1 photon. Now it's rude, but of course that's one of the choices. So if you picked 4.4 times 10 to the negative 19th. Oh, you were so close. I mean, you didn't do anything wrong. We just missed the last part. I want to know the energy of a mole of photons of blue light. Oh, dang. Okay, so now we got to do one more little switch. That I had joules per 1 photon, but there are 6.022 times 10 to the 23rd photons per mole. And there are 6 times 10 to the 23rd particles per mole of anything. And so now all I have to do is multiply. And now I get my final answer in units of joules per mole. Whew, that's a lot of work, huh? For your response, you want a calculator for this. And it takes a couple steps. So obviously we want to be able to show our work in a free response question so that if by chance you had a brain fart and you got the wrong frequency, but maybe you did everything else right, now we can award you partial credit. Or maybe you forgot to switch the nanometers to meters, but you did everything else right. Well, that deserves partial credit. As long as you showed all your steps, your work was labeled with units, all the steps were shown. Then if you make a little misstep along the way, it's easy for the grader to find that and understand that you carried it through correctly. But this is the worst that it ever gets. This is it. This is the calculations. Now, obviously, we could also go backwards, and we could say, hey, I have this much energy per mole of photons. I could divide by 6.022 times 10 to the 23rd to figure out how much energy that is per photon. If I had the frequency, I should say if I had Planck's constant and the energy, I could solve for frequency, which then I could plug into the first equation and solve for wavelength. So you could do this backwards, and maybe they would say like, hey, what kind of radiation is this? Or maybe this is light in the visible spectrum. What color would this be? And we would go through this series of calculations backwards. And maybe they start you off down here. Then I could go backwards, and I could find the energy per photon. If I had E energy and Planck's constant, I could solve for the frequency. And if I had the frequency, and then obviously I would have the speed of light, I could solve it for the wavelength. And then obviously I would be given like an electromagnetic spectrum, and I could solve for the color of light. I could just match it up, kind of like here, and say, oh yeah, that would be visible blue light. Crazy, crazy. And the last couple have to do with these different effects of energies at different parts of the electromagnetic spectrum. And again, it's nothing to get your undies in a bundle about, but it might be one question on the AP test. And if I get that one question right, fantastic. This would be a short, easy question, hopefully. In a nutshell, here's the deal. This region X, ultraviolet visible light, of the different types of radiation shown here, this is high energy. And then down on the other end of the spectrum, my microwaves, radio waves, these are low energy. Okay, so the highest energy, the ultraviolet and the visible light, that will cause electrons to transition amongst the energy levels. And that's why we see visible light, and we don't see the ultraviolet, but we can detect ultraviolet radiation when we do like flame tests, where, oh my gosh, I added energy and I can see evidence that the electrons moved and transitioned up and down the energy levels, even though I can't see electrons. But when I see that red visible light being emitted, I can infer that the electrons gained smaller amounts of energy and released smaller amounts of energy. And that energy released is in the form of like visible red light, or it could be in the form of visible violet light, where then I know the electrons made larger transitions. Now, obviously, the amount of energy can cause different types of transitions, 1 level, 2 energy levels, 3 energy levels. But it seems that for most elements and most atoms, we need at least energy in the visible light spectrum to cause those electrons to transition up the energy levels. Now, in the middle, the infrared, that just causes molecules to vibrate, causes molecular vibrations, and the lower energy, like microwaves, will cause molecular rotations. And we'll learn about like the vibrations and the rotations more when we do bonding, but rotations are like the least intrusive of these changes. If I talk about electrons moving up and down the energy levels, that's kind of a big deal. And molecules vibrating will eventually help us learn about what type of bonds are present. But rotation is pretty non-intrusive. There are certain types of bonds that can rotate, but I mean, it's not like we're breaking bonds, we're not changing any electron energy levels. It's a pretty mild change to a molecule if all we do is make the atoms rotate in their bonds. Two other questions that are kind of along the same lines are 7 and 8, just to kind of show you what has been put on the AP test in reference to this type of question. Something like 7, nitrogen molecules absorb ultraviolet light, but not visible. Iodine molecules absorb both visible and ultraviolet. Which of the following statements explains the observation? It should be the third. Visible light does not produce transitions between electronic energy levels, like electron energy levels, in nitrogen. So visible light's not enough energy to cause the electrons to move up and down the energy levels in nitrogen, but it does produce transitions in iodine. And now eventually, in the next unit, we'll kind of learn maybe why that is. That nitrogen is a pretty small atom with the electrons pretty close to the positive nucleus. And so when the electrons are pretty attracted to the nucleus, it's just going to take more energy to make those electrons transition up the energy levels. So it kind of makes sense that with a smaller atom, I probably need a little bit higher energy to cause electron transitions. But iodine is a huge atom, and so visible light is plenty energy to cause electrons to transition in iodine. And finally, question 8. Infrared spectroscopy is a useful tool for scientists who want to investigate the structure of certain molecules. Which of the following best explains what can occur as the result of a molecule absorbing a photon of infrared radiation? So infrared means below red, a little bit less energetic than visible red light. And we're looking at the second choice. The energies of infrared photons are in the same range as the energies associated with different vibrational states. There's the key word. Infrared causes molecules to vibrate. Now eventually that's going to help us to understand what types of bonds might be present. Molecules can absorb infrared photons of characteristic wavelengths, thus revealing the types and strengths of different bonds in the molecule. So strengths, single bonds, double bonds, triple bonds, all that good stuff. But we can get some of that information by looking at how much energy is required to make these bonds vibrate. And it does seem to fall in this infrared part of the electromagnetic spectrum.